Good morning, everybody. Today we're going to look at the time response of second-order systems. This is a continuation of lecture 16. And now we're going to do the same analysis for second-order systems. And this is probably one of the most important lectures, because in this lecture, we're going to see how a system can be characterized based only on the location of its poles. All we need to know to understand how the system responds in the time domain is to look at where the poles are placed. And depending on where they are, on the real axis, on the imaginary axis, or having both the real and imaginary parts, we can infer exactly how the time response will be. And then in the next lecture, we are going to quantify that time response in terms of some metrics that we're going to come up with. But today, we're going to see how the poles, the location of the poles will influence the time response. So we started this in the last lecture. It's basically a continuation of it. And here is the basis of all our analysis. We identified these two different phases here in the time response. The first one is the transient response. The second one is the steady state. The steady state, we know how to calculate that. We can simply use the final value theorem. And the transient response is that time the system takes to go from zero, from rest, from time a input is applied to it, up to the point where it reaches a steady state. Now, as you can see here, there are many different shapes that transient can take. In the last lecture, our transient was limited to a exponential curve. Right, was just that exponential curve. And the reason was that it was a first-order system, and first-order systems have only real poles. The poles are always on the real axis, right? And because of that, then the inverse Laplace transform cannot show any exponential sinusoidal component. It will only show exponential components. So you're limited to this shape, or of course, a shape that goes to infinity if the system is unstable. But now when you deal with second-order systems, we have a second-order transfer function, polynomial in the denominator of the transfer function. And that can now have complex roots, could have real roots, or could have a combination of them. So the shape of the time response may take now sinusoidal components, right? Because you remember that the complex part of the pole determines the sinusoidal component of any time response. So now we may have a combination of these two. So let's see that part today and focus on. And then in the next lecture, we're going to quantify this time response in terms, for example, of overshoot, how far it goes up before it settles, how long it takes to settle, and so on. And once again, that can be done based only on the location of poles. The advantage is that we don't even need to take the inverse Laplace transform to understand how a system responds. We can simply look at its transfer functions, look where the poles are, and that is sufficient information to infer its time response. So let's get right into it. So this lecture is going to be a bit long, but it's very important. So if you have any questions along the way, just stop and ask me, okay? We introduced a standard form for a first-order equation in the last lecture. So here is the standard form for a second-order equation. So the first thing we notice here, of course, is that the polynomial in the denominator has an order of 2. So we have a second derivative. We have a second-order differential equation. Another thing that we see here, we have these two new variables, zeta and omega n. So the standard form for a transfer function will always take this formulation, s squared plus 2 zeta omega n s plus omega n squared. And you have also omega n squared on top of the equation here. This is just to make the system in a way that when the unit gain, the gain of this transfer function is 1. If you find the limit for a step input, for example, when you make s tend to 0, it always results in 1. So it's just to normalize that, right? But that doesn't influence the shape of the time response. It's just a constant gain. So this is the standard form. And what we see here, zeta is what you're going to call the damping ratio. And omega is you're going to call the natural frequency of that transfer function. Zeta is dimensionless, has no units. And the natural frequency is a frequency, so it has a unit of radians per second. And why are we writing the function in this way? Where does that come from? Well, as we will see, zeta and omega n are the two variables that we need to describe the system time response. And by analyzing, for example, the value of sigma, the value of zeta, we can determine which shape the system will have in the time response. By analyzing the natural frequency, we can tell how much is going to oscillate. Right? So these two values, they are not random. They come there. They are here because they are the elements that will characterize that time response. So we'll see how they influence the time response. For some of you who have taken electrical circuits, you have probably heard of underdamped, overdamped, and concepts like that. Is the same thing here. Is exactly the same concept. Okay, so these are the two components we need to highlight in the transfer function: the damping ratio, which is an indication of how much energy is being dissipated in the system, and the natural frequency, which frequency the system would oscillate if let to oscillate in the case where there is no damping. So the natural frequency, in other words, is the frequency the system would oscillate without damping, the frequency of undamped oscillations. Right? And the damping ratio is a characterization of how much energy is being dissipated in the system. Just give me 1 second here, and I'll block the rotation. Now, because you have a second order system, we can equate this to 0 to find the roots of this polynomial, which are the pole of the transfer function. And now we know that this second order transfer function can have real numbers as poles, can have complex conjugate numbers, so have both an imaginary and a real component. Or it could be a purely imaginary pole. How does that now affect the time response, as you're going to see? So to give an example here of second order system, we can consider this mass spring damper system. The input here is the force, and the output is the displacement. If you find the transfer function between the force and the displacement, we get h of s at the bottom here. All right, nothing new there, 1 over ms squared plus bs plus k. And now we can identify the damping ratio and the natural frequency of this mass spring damper system by comparing this function with equation 1, which is the standard form for that. Now, the first thing we need to notice here is that in the standard form, s squared is multiplied by 1, whereas our transfer function is multiplied by m. We need to get rid of that m first. We can multiply the whole, just put m ahead of the function, so factor it out. And then you have s squared plus b over m s plus k over m. Right. And what else can we do now? Well, now we can compare the coefficients of transfer functions here. So these two are equal. That's good. It's 1 and 1. 2 zeta omega n multiplies s, and what multiplies s here is b over m. And omega n squared is the one that multiplies s to the power of 0, which is equivalent to k over m. So we know that omega n squared equals to k over m. So omega n is square root of k over m. We also can equate now 2 zeta omega n to b over m. And then let me just find some room here. We can calculate zeta as b over m over 2 times omega n, which is square root of k over m. And you may ask what happens to that omega n squared on top, right? Well, that is not necessary. That's a gain. If you want to put it in there, we can simply write omega n, we can write k here and the k at the bottom. All right, so here is our omega n squared, 1 over k over m on top. So all we did was to add this gain to in front of the transfer function, that is 1 over k times m. Right? But what we are interested in is the location of poles. So what is on top of the equation is just a gain that amplifies the magnitude of the response, but does not change the shape of that response. Right? So it has no influence. So for consistency, if you want to really write that in the standard form, then simply put a k on top there. So now we have k over m. Right? And then divided by k, so we don't change the magnitude of the function. And then you can identify your omega n there as well. So through this example, we get both zeta and omega n. You can see now that zeta, the damping ratio depends on friction in the system. And you can see the natural frequency depends on the mass and on the spring coefficient, which makes sense. Right. So if we let this, for example, we remove the damper and you let this mass oscillate, it would oscillate at a frequency that is square root of k over m. Would be the frequency of oscillations when damping is not there. That characterizes the natural frequency. How much energy is being dissipated in the system? That's an indication of zeta. And you see that is directly proportional to B. Any questions so far? No? Okay. All right, so we know how to identify these zeta and omega n is just comparing the coefficients of different functions. Now let's look at where the poles of this function are. If you have a quadratic function here, s squared plus 2 zeta omega n plus omega n squared, we can simply equate that to 0 and use the quadratic equation to find the roots. So here's the quadratic equation, that's the roots of that, minus 2b plus minus b squared minus 4ac divided by 2. That's what we got. And the result of that, you can simplify all this, is given in equation 3. 2 zeta omega n squared is 4 zeta squared omega n squared. We take omega n squared out of the square root. We take also 4 out of the square root. That's 2, and then it cancels out with the 2 at the bottom. And this is the result. Very simple math. And we could, so you have a square root here. And this is square root. You can see now that depending on the value of zeta, the result inside of that square root might be positive or negative. So if you have a positive result, we have real numbers. If you have a negative result inside the square root, now we are starting to see complex numbers in the solution. To highlight that better, I could multiply everything here by square root by -1 and by -1 again. And the square root of -1 is j. So I can take j to the front of the equation. And then everything that is inside is flipped. I just multiplied by -1, so I'm multiplying by 1. Doesn't change anything. But now I take the square root of -1, which is j. One of the negative ones comes out of the equation of the square root, excuse me. That's the j in front here. And now you see that the sign flips inside. These two representations are exactly the same. Exactly the same. The reason I'm presenting the second one is that you can clearly see here the poles now may have a real and imaginary part. The real part is omega n times zeta, negative omega n times zeta. And the imaginary part is omega n times the square root of 1 minus zeta squared. So these poles can now be placed on the imaginary on the S-plane as having both a real and imaginary component. So the real part is negative zeta omega n. And the imaginary component might be omega n, negative omega n, square root of 1 minus zeta squared, and plus omega n, square root of 1 minus zeta squared. Notice here that the complex part is always in conjugates. You cannot never have a odd number of complex numbers. It will always be in pairs. Right? You always have the complex conjugate of something. Okay, so here are the potential locations of these poles. And you can see that these values, these dots there, will travel on the S-plane, now depending on the value of zeta and depending on the value of omega n. Are there any questions up to this point? No? All good? Yeah? Any questions from home? I have a question here. If I can change the video window, I can't. It's set up here and I have no control over it. But I'll make sure that if there's anything under the video, I'll remove it. Okay, so again, all I did here was to highlight the real and imaginary components and then plot that in here. So do you see that these two are the same equation? You see what I did there? Just multiplying things by -1 by -1, and then I took the -1 square root of -1, which is j, out of the equation, and then what was left inside is multiplied by -1. Yeah. Okay. So that's to say that now we may have complex and or real numbers, and what is going to determine that is the damping ratio, because you see inside the square root, all we have is the damping ratio square minus 1. So depending on the damping ratio, we might see complex numbers. And now you understand why we want to write the transfer function in the standard form that depends on these two values, because they are the ones dictating how the time response is going to be. If you end up with complex numbers or real numbers, well, the time response is different because one has exponential components, the other one doesn't. And that only depends, on this case, on the damping ratio zeta. So that's where it comes from. So now we need to analyze 3 cases, or like 4 cases. Well, let's do them one by one. So the first thing you can notice here, if it's zeta is greater than 1, then we get zeta squared minus 1 is being greater than 0. If zeta is greater than 1. You also notice that every time I write zeta, it comes out differently. I've been teaching using this for years, and I still don't know how to write it. So if zeta is greater than 1, zeta squared minus 1 is greater than 0. The result inside the square root is a positive number, which means that we have real roots. Poles are real. So the first case you're going to study is what we call the overdamped system. In an overdamped system, there is lots of damping. And that is characterized by having the damping ratio being greater than 1. Remember the case of the mass spring damper system. The damping ratio was directly proportional to the damping in this system. So here, if you have a zeta greater than 1, there's lots of damping. And the damping is there to dissipate energy. It's going to dissipate everything fast. The result of that mathematically is that the poles are only real number, are 2 distinct real numbers. Right. So because of this, now the roots are negative real numbers. And another important point here to note is that they are negative, right? Because we have omega n, negative omega n times zeta. And what comes out here is a positive number. So the result that is smaller than zeta, the result is always a positive, a negative number. So the result is 2 real numbers that are different and they are negative. So if we have 2 roots that are real, we can take our transfer function and write that in the form of let's say s plus a1 times s plus a2. By just splitting the polynomial into 2 real roots. And then take partial fraction decomposition, and the partial fraction decomposition will result in something like that. K over s plus a1, k2 over s plus a2. And when we take the inverse Laplace, what do we see? We see that the result is an exponential waveform. That's the first observation we can make. And we can also see that the coefficient here of t is negative, meaning that as t grows, as t tends to infinity, these exponentials decay to 0. And therefore, the system converges. It will settle at a given point, same as the first order system we saw. Remember, depending on the value of the pole, if the pole was on the left or it was on the right side, these exponentials wouldn't converge. Here is the same story. For a overdamped system, lots of damping, poles are real numbers, distinct real numbers with negative real parts, and therefore the inverse Laplace transform gives exponentials that are decay to zero and the system settles. Are we good? This is very similar to the first order system. It's the same type of time response. Here are some examples. So I'm now just giving random values for the mass, the spring, and the damper. Mass is 1, spring coefficient is 1, and then I'm changing the damping. And by changing the damping, B, coefficient, I'm changing the damping ratio. You see that as I decrease B from 3 to 2, the damping ratio is decreasing from 1.5 to 1. And look what is happening in the time response. So here I have the time response and the location of two poles. First thing to notice is that the poles are distinct real numbers placed on the negative real axis, and the response is an exponential. As if I keep decreasing the damping ratio, we see that now the poles are getting closer together, and you see that this pole is getting away from the imaginary axis, which results in a faster system. Remember the time response story from the last lecture? You're getting away from the imaginary axis. The system is settling faster. And I can keep decreasing this damping ratio up to a critical point where the damping ratio is exactly 1. And when the damping ratio is exactly 1, we see these two poles meeting at the same point here. They are the same. And at that point, we still have an exponential curve, right? Exponential over there. Okay. So as we decrease the damping ratio, the system responds faster up to this critical point. You see the poles coming together as the damping ratio is decreasing, and they're going to meet at some point. This particular point where the poles meet is a critical point because that's the transition to a different time response. And that's where we call a critically damped system. In a critically damped system, we have, as the second case of interest, here we have zeta equals to 1, precisely 1. Now let's look at our equation. When zeta equals to 1, this is 0, this is 0. We have S1 equals to S2, which is negative zeta omega n. So both poles are equal real numbers. If these poles are both equal real numbers, we can write our function. Remember that it was 1 over S plus A1 times S plus A2, but now A2 is the same as A1. So this is the same as 1 over S plus A1 squared. These are real roots minus A1 are the two poles. They are the same. When you take the inverse Laplace transform, we'll have to do partial fraction expansion. This will require two functions like that, K1 plus K2. We can take the inverse Laplace. Here is the response. Again, an exponential waveform that is indistinguishable from the overdamped system. You see back here, the last case is a overdamped system because the two poles are the same. We can't tell by visually inspecting the time response if the system is overdamped or overdamped because they look exactly the same. It's just an exponential curve. Another interesting observation we can make here is that because these poles have negative real parts, they are placed on the left side of the S-plane. You see all exponentials here with a negative coefficient, meaning that as time tends to infinity, the coefficient, all the exponentials will decay to 0 and disappear. Okay. So let's recap the two cases we did. The first one is the overdamped system, lots of damping, zeta is greater than 1. That results in two distinct poles. Poles are real numbers and poles are negative real numbers. They are placed on the left side of the S-plane. And the result is exponential. As we decrease the damping ratio, the poles are starting to move towards each other. They are going to meet at some point, and when they meet, they are the same. That is what characterizes a critically damped system. Two real numbers, two negative real numbers, those are the poles. The result is still a exponential waveform. And why am I calling that a critical point? Well, it is critical because if we keep decreasing the damping ratio further, we are now starting to see oscillations. And we can see that from the equation. Let's go back to our equation here. This is case number 3. Now the damping ratio is smaller than 1. And if it becomes smaller than 1, we can see that a zeta squared minus 1, it becomes smaller than 0. For zeta is smaller than 1. The result of the square root here is a negative number, meaning that the square root of a negative number is now a complex number. And we ended up here with a complex conjugate pole. Here is the real part of the pole, and here is the complex part of the pole. And the only difference between them is now of course, the conjugate of the solution here. So real part and imaginary part. So in this case, we call this type of systems the underdamped system. Why underdamped? Because now the damping ratio is between 0 and 1. The time response will change because now we see the exponential component there, but we also see an imaginary component in the poles. And if you remember from the definition of the Laplace transform, the imaginary part is what gives rise to the sinusoidal components in the time response. Now, when you do the inverse Laplace transform of this is the sort of equation you're going to get. We did some examples like this in class. Remember when we had something like s squared plus s plus 3, we had to write this as s plus 0.5 squared plus something, and that the result was an exponential times a sinusoidal. Remember, we did that a few times, and the reason we had to do it that way is that for this particular equation we cannot do partial fraction expansion with real coefficients in the denominator because the poles are complex numbers. All right. So this is just a more generic representation of that approach. And anytime we have solved it, we see now two components showing up here. The first component is an exponential component, and this exponential component comes from the real part. And the second component here is the sinusoidal component that comes from the imaginary part. Same as the Laplace transform definition. Another thing that we see here is that the real part of the pole is negative. Look, the real part of the pole is negative zeta times omega n. Zeta is between 1 and 0. So this is a negative number, meaning that the real part of the pole is still negative, is still placed on the left side of the S-plane. And you can see that in the exponential still has that negative coefficient, and will eventually decay and bring the sinusoidal to 0 as well. Right. So the good news is that, well, despite the fact that we have some oscillations that is coming out from the sinusoidal component, the real part of the pole is still negative, meaning that the exponential will be negative and the whole thing will eventually go to 0 and settle at some point. So the system converges. Here are some examples. You see that I'm still decreasing B, and by decreasing B, I'm decreasing zeta, going from 1.5 to 0.1. And see that zeta is getting very small, up to 0.05. And look what is happening. As soon as we go below 1, in the first graph there, we see a little bump. That's not an exponential. That's the sinusoidal component starting to show up. And look where the poles are. The poles now broke away from the real axis, and now they became complex conjugate numbers. They have both a real and imaginary component. The real component is negative, is on the left side of the S-plane, and that brings the exponential to 0. All right. And then you can see that because this is a step response, the system is settling at a given point. Now let's continue to decrease B. We see in the second graph there, the poles are still complex conjugate numbers. You see that now the oscillations are getting higher. The oscillations are getting higher, and you can also tell that the poles are moving towards the real axis. And as they move towards the real axis, what is happening? They are becoming slower. Their response time is decreasing. Is increasing. They are taking more time to decay. Same as what you saw in lecture 1. They're getting closer to the imaginary axis. So they let the sinusoidal operate for longer. Let's see it that way. Right? Because they are slower. They take more time to decay. And the same continues as we keep decreasing the damping ratio. If you go to the third and fourth graphs, you can see the poles as the damping ratio decreases. You can see the real part of the poles moving towards the imaginary axis. The poles are becoming slower. The exponential is becoming slower. So the sinusoidal component operates for longer, right? Because it takes more time for it to decay. And then eventually we may reach the imaginary axis. So this is the third case. These are the underdamped systems. Underdamped systems, the damping ratio is between 0 and 1. Overdamped, lots of damping, damping ratio greater than 1. Critically damped is a transition between the underdamped and the overdamped, where the damping ratio is exactly 1. And then the underdamped system, the damping ratio is smaller than 1, but greater than 0. And you see these oscillations. But again, because the poles are still on the left side of the S-plane, the exponentials converge, they decay, they die off to 0. Are there any questions so far? No? Okay, so let's see if you're following. Here is a question. What happens if the damping ratio is 0? Somehow it becomes 0. It keeps oscillating, exactly. Why is that? No damping, no damping. Very good. Now, if you think about the time response, the Laplace transform, how would we see that in the Laplace transform? The exponential component disappears, and you are left with only imaginary poles placed on the imaginary axis. No exponential, no way for the sinusoidals to decay. The exponentials are what make the sinusoidal decay to 0. The exponentials are not there. The system is free to oscillate forever. So that's case number 4, no damping. No damping in this case of the mass spring damper system implies B equals to 0. It's just a mass spring system. So hypothetically, if there is no damping, zeta is 0. What do we see here? Zeta is 0, so we have 0 here, and we have square root of -1 there. Square root of -1 is j. This becomes omega n times j, and this also becomes, negative omega n times j. Aha. See omega n here? The natural frequency, the frequency of undamped oscillations. That's where it comes from. When zeta equals to 0, there is no real part. The poles are purely imaginary numbers. They come in complex conjugates as always. But you see the sigma, the real part, is gone, is not there. If you think about the Laplace transform of this, The Laplace transform would tell us, because you have only imaginary numbers in your poles, the signal you should expect from this is only sinusoidal. There are no exponentials. And that's precisely what happens. That's precisely what happens. So let's look at the way the transfer function is rewritten here. Is rewritten as a function of poles. We can, of course, write the poles as imaginary numbers. And when you multiply that out, we have omega n squared divided by s squared plus omega n squared. And you see that the roots here are only complex. Right? We have to do s squared equals to negative omega n squared. And then you go back to what you had there. S equals to square root of negative omega n squared, which is j times omega n, plus minus. If you apply a step input to the mass spring damper system and you do the inverse Laplace, we get the last equation there, h of t equals to 1 minus cosine of omega times t. And this makes sense because when there is no damping, nothing dissipates energy in the system. If I apply a step to the mass, I'm now accelerating the mass, giving a kinetic energy. That kinetic energy, it stretches the spring, which stores now potential energy. So kinetic energy is transferred to the potential energy. Potential energy is transferred back to kinetic. In the process, nothing dissipates energy. So the system oscillates forever. Unlike the other three cases, where in the process of transferring energy from one form to another, there was a damping dissipating part of that energy, and that makes it decay to zero. That's gone here, so the system is free to oscillate indefinitely. And here is the result. B equals to 0, no friction, entails zeta equals to 0, and here is the step response of the mass spring damper system. What is happening? We see oscillations that don't decay because the exponential part is gone. And if the exponential part is gone, the poles are purely imaginary numbers. They lie on the imaginary axis, as we can see here. They lie on the imaginary axis. And this system is oscillating now at its particular natural frequency, omega n. And in this particular case, omega n is, as we calculated before, is square root of k over m. Now that's where the natural frequency definition is. The natural frequency is the frequency of undamped oscillations. And this makes sense. If we increase the mass, we decrease the frequency of oscillations. Think about a mass connected to a spring. The greater the mass, the more time it will take to go back and forth, right? So if we increase the mass, we decrease the frequency of oscillations. If we make the spring stiffer, then the faster it will oscillate. Okay. And we can now, if you change k or m, the natural frequency will change, meaning that these poles will have to travel along the imaginary axis. The distance of the pole to the center is the natural frequency. So if you change the natural frequency, the pole will start to go up and down. This is what is happening here. First example we had before, and now here B is still 0, but I'm changing the mass. The spring is kept at 1 Newton per meter, and I'm changing the mass. And you see that as I change the mass, I'm changing the damping ratio. Excuse me, I'm changing the natural frequency. By increasing the mass, I decrease the natural frequency, and then the poles move downwards. They move, or they move towards the center of the S-plane. All right, so we can now control the frequency of oscillations by making these poles translate here. We can change the shape of the time response by making the poles move along the imaginary, the S-plane by changing B, the natural, the damping ratio. Okay. So we went from, let's recap, from a overdamped system, zeta greater than 1, exponential response only. critically damped system, zeta equals to 1. 2 real poles equal the same point, it's still exponential. Zeta between 0 and 1, poles are now complex conjugate numbers. We have both sinusoidal and is exponential. When zeta is 0, only sinusoidal, the poles lie on the imaginary axis, the system oscillates indefinitely. And that's to say, once again, that what makes the energy, what dissipates energy here is the damping ratio is related directly to the exponential components. And so far, for everything we did, we ended up with poles. If they have a real part, the real part is negative. The poles are on the left side of the S-plane, which means that in time domain, all exponentials that come from this real part of the pole decay to 0, and the oscillations eventually stop, except for the case of a undamped system, which is this one, where the damping ratio is 0. Nothing is there to decay, to make the energy dissipate. Any questions? Any questions? No? Okay, so you have a last case study here, the unstable system. And this would occur when zeta is less than 0, smaller than 0. In the case of the mass spring damper system, this would imply having a damper with a negative viscous friction coefficient, which is physically impossible. If you can think of a way to create a negative damping, patent it, because that's basically free energy. That's not going to happen, but that's mathematically possible to have a damping ratio smaller than 0. And when we do that, we can see here that when the damping ratio is smaller than 0, the real part of our poles now become positive when zeta is smaller than 0. We put a negative number for zeta there, and now the real part is positive. If the real part is positive, we don't even need to bother about the other parts of the system. Because what happens when the real part is positive? Remember from the first order system? Now exponentials grow to infinity. And if exponentials grow to infinity, it doesn't matter if it is an exponential or an exponential plus a sinusoidal, everything blows to infinity. Right? For a positive real, for a negative damping, for a negative damping ratio, then the either real or imaginary roots will have positive real parts. And when they have positive real parts, the exponentials increase to infinity. The system is unstable, it never settles. We have two possible solutions here, one for zeta between 0 and this is zeta is smaller than -1, and this one here is zeta between -1 and 0. We have exponentials or exponential and sinusoidal depending on the value of zeta, but in both cases we notice the problem here is that the exponentials have positive coefficients, and so long as one of them has a positive coefficient, everything else blows to infinity. So long as we have one pole with a positive real part, the entire system is unstable. So even if our system has 50 poles, 49 of them are on the right side, the left side of the S-plane, and one is on the right side. One has a positive real part. That is sufficient to take the entire system to instability, to infinity. All right, so in this case here, the exponential components increase with time, and the system is said to be unstable. And that's the last case we need to consider. Are there any questions about these 5 cases? No? All good? Here is the result of that. We see now that when zeta is negative, B is negative here, we are entering, still have complex poles for this example, but now the real part is positive. We enter the unstable zone. We are on the left side, excuse me, the right side of the S-plane. The exponential goes to infinity and brings the sinusoidal with it to infinity. If you keep decreasing the damping ratio, the poles may go back to the real axis, only real, but now they are positive, and then the exponential grows to infinity, and the system is unstable, same as the case for the first order system we saw in the last lecture. So let's do a summary here of everything. Poles and the transient response. So the first case we had was two distinct real poles. And this case was for zeta greater than 1, what we call the over-damped system. Two distinct real poles. But in the real part is smaller than 0. When that happens, the time response is only an exponential waveform. So long as the poles are lying on the negative real axis, that's what we should see. That's case number 1. Case number 2 was when these two poles met somewhere. So we have zeta equals to 1. We have a critically damped. And the real part, so we have two identical real numbers as poles, but the real part is still smaller than 0. And that is case number 2. It will also result in an exponential waveform in the time domain. And visually, there is no way to distinguish the overdamped from a critically damped. The third case was now when we keep decreasing the damping ratio, and now we have zeta between 0 and 1. Now zeta is smaller than 1. This is a underdamped system. We have two distinct imaginary numbers or complex conjugate numbers. The real part is still smaller than 0. So we are here and here. And this will result in a sinusoidal times an exponential. Right? The exponential comes from the real part. The sinusoidal comes from the imaginary part. So long as the real part is negative, the exponentials decay and the system settles. We can continue now, and if we keep decreasing the damping ratio, we reach the next case, which is the undamped system, where the damping ratio is 0. We have two distinct imaginary numbers as a result, and the real part is 0. So the system settles here and there. There is no exponentials because the real part is 0. And the result is a oscillatory behavior that never stops. Okay. And then the last case is when the poles enter the unstable zone. When we enter the unstable zone, the real part of the pole is greater than 0. Exponentials decay, don't decay, they blow to infinity. Sorry, just 1 second here. They blow to infinity, and they bring with them any sinusoidal component that might be there. So in the first case, we have poles that are still complex conjugate numbers. For this poles here, we have the damping ratio between -1 and 0. That's the result. And then the last case is where the poles go back to the imaginary axis. This requires zeta to be smaller than -1. And this gives a growing exponential to infinity. Okay, but it doesn't really matter because these systems are unstable. Both are unstable. Both have a positive real part. As a result, exponentials grow to infinity. If there is any sinusoidal component there, that also blows to infinity. Okay, so for a system to settle or for a system to be stable, the real part of the poles, all poles, must be negative. So long as one pole has a positive real part, the entire system blows to infinity, doesn't settle. Any questions? All good? All clear? Has anybody heard of underdamped, overdamped system in electrical circuits before? Yeah? It's the same idea. Okay, but also apply to mechanical and whatever system we are studying. Any questions from home? Anybody has questions? You can type it. No? All right. No questions. Let's do an exercise here. Very quick exercise. We have the force displacement of the mass spring damper system we saw before that is given by the following transfer function. So we identify here the mass with 1 kilogram. We identify the spring coefficient, which is 9. And we also identify the damping coefficient B. B plays an important role dissipating mechanical energy and strongly affects the temporal response of the mass when subjected to a step force input. The mass is going to be subjected to a step force input. Calculate and sketch the response to a unit step input for the following cases: B equals to 9, 0, 2, and 6. So let's do that. So here is case number 1. B equals to 9. Notice here, this is the step input. Now you may say, oh, we ended up with a third order system. Well, not really. We have a second order system subjected to a step input. That's not a third order system. Okay, so we want to sketch the time response. To do that, what do we need to figure out? We need to know the damping ratio, so that will tell us the shape of the time response. We need to know the natural frequency. Our standard formulation for the second order system is omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. Now we can equate the coefficients. We see that the coefficient of s is 1. That's good. The coefficient of s squared, sorry, the coefficient of s is 9 and 2 zeta omega n. And the coefficient of s to the power of 0 is omega n squared. So with this, we can write that omega n squared equals to 9, and omega n is 3 radians per second. And this is for all values of B. It doesn't depend on B. For all values of B, we have the same response. I don't need to calculate this for the other cases. What is zeta? We can say the 2 zeta omega n equals to what? 2 zeta omega n equals to? What is 2 zeta omega n equal to? 9. Right? 2 zeta omega n equals to 9. Yep. So we have now zeta equals to 9 divided by 2 times omega n, which is 3, and this is 1.5. What system do we have here? Overdamped, underdamped, critically damped, or unstable, or undamped? Zeta is greater than 1, and therefore this is a overdamped system. If it is an overdamped system, this tells us that the roots are real numbers. So if I find the roots of this, put it in a calculator, we'll find S1 equals to negative 7.845 and S2 equals to negative 1.145. This means that h of s can be written as a function of these roots, s plus 7.845, s minus plus 1.145 times 1 over s. This is again is the input. And what do we do now? Partial fraction. Right? These partial fractions can take the form of a over s plus 7 plus b over s plus 1 plus c over s. Right? So I'm going to skip the partial fraction because it's not the focus of today's lecture. I'm going to just give the result here. It's going to be 1 over s minus 1.117 divided by s plus 1.145 minus plus, 0.171 divided by s plus 7.845. If we can now take the inverse Laplace transform, the inverse Laplace transform is 1 minus 1.17 exponential of negative 1.145t minus 0.171 exponential of negative 7.84t. You can plot this, and if you plot it, h of t as a function of time, we can see that this settles at 1 and reaches 1 following an exponential function. Okay, let me summarize it here so you can keep track of what we are doing. So this is the imaginary, this is the real, and for case 1 we have negative 0.7 point, how much was it? 78 and negative 1.45, and this gave that sort of time response. This is case number 1. That was an exponential time response. Any questions for this one? Yeah. Sorry, I can't hear you. Radians per second, yeah. For all, that's the sign for all. B, for all B. Yeah. Just to say that the natural frequency is independent of B in this case. Any questions? Shall we move on? Yeah. Okay. Next case here, we have B equals to 0. B equals to 0, no damping, no coefficient of viscous friction is 0. We simplify the equation to this. So zeta is 0. 2 zeta omega n equals to 0. And we have still omega n equals to 3 radians per second. We have s squared plus 2 zeta omega n s plus 9 plus omega n squared. Omega n squared is here, and this is 0. So zeta equals to 0. So what do we have here? We have 2. If you find the roots of this equation, you have s squared plus 9 equals to 0. That's s equals to plus minus 3j. Those are the only possible solutions for the damping ratio. So we cannot split this into real numbers. We only have complex numbers in the solution. So this needs to be dealt as such. So we have now a partial fraction that will have to be written in the form of as plus b divided by s squared plus 9 plus c over s. And I'm going to give you the coefficients of the partial fraction here, minus 1, 0, and 1. If you can solve this with whatever method you like, and you can find h of s as 1 over s minus s divided by s squared plus 9. What is the inverse Laplace? H of t is 1 minus sine or cosine? Back to lecture 5. Inverse Laplace of s divided by s squared plus 9 is cosine of come on, folks, 3t. Very good, thank you. 3t. Aha, see, 3t, the natural frequency showing up in the frequency of oscillations there. It is oscillating, and is oscillating at 3 radians per second, which is precisely the natural frequency. We can plot this. T and h of t. When time is 0, cosine of 0 is how much is it? 1. That's 0. And when we have 90, that's 1. I have negative 90, that's 180, that's negative 1. So that goes from 1 to 2. Starting at 1, oscillates like that. So you are basically applying a force, and we displace it. That's what the shift comes from. And then it oscillates around that shifted position because you're applying a force to it. So let's go add this to our summary here. In the second case, we have plus 3g. And we have negative 3g as the poles. And this resulted in a sinusoidal component. Any questions? No? Okay. So if there are no questions, let's do now the case where b equals to 2. Back to the standard form, omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. We already determined that omega n is 3 radians per second. And now we can say that 2 zeta omega n equals to 2. So zeta is 2 divided by 2 times 3, which is 1/3. That's smaller than 1. which characterizes what type system? Characterizes a underdamped system. Underdamped system. This means that if you attempt to find the roots of this polynomial, the roots will have both exponential and sinusoidal components. They will be complex conjugates. And indeed they are. If we do s squared plus 9s plus, plus 2s plus 9 and do equate that to 0, we'll find that s is -1 plus 2 square root of 2j, and s2 is -1 minus 2 square root of 2j. So we cannot split this s squared plus 2s plus 9 into a partial fraction with real numbers. We could do that with complex numbers and do the partial fraction decomposition using complex numbers. That's not a problem, but it will take a lot of time. We still need to do partial fraction though. So what we can write is as plus b over s squared plus 2s plus 9 and plus c over s. I'm going to give the coefficients here because this is not the focus today. If you have trouble finding them, send me a note. I will give you the full solution. So h of s in this case can be written as 1 over s minus s plus 2 s squared plus 2s plus 9. And now we need to find the inverse Laplace of this. Do you guys want me to go over the entire inverse Laplace, or are we good with this sort of? This was in like 2-3 assignments. Do you want me to go over it? I can just give you the inverse. Yeah? Does anybody at home want me to do the inverse, or can I just give you the final answer? Okay, so if I hear nothing, I'll just give you the final answer. I'm going to write just the generic form here. What I would do is s plus 1 squared plus 8 in the denominator, and then you have s plus 1 on top. Does that ring a bell? Yeah? So now I can split that into two functions. One will become an exponential times a sine. The other one will become an exponential times a cosine. You probably remember that from the assignments. So I'm going to stop here. I'll just give you the full, I'll give you the full solution later in the annotated lecture notes. But for now, I'll save some time. I'm going to give you h of t here, which is 1 that comes from 1 over s, exponential of minus t, cosine of square root of t minus 1 over square root of 8, exponential of negative t sine square root of 8t. We can plot this, and because this is a step response, this is tending to 1. This is h of t, and this is t. It's tending to 1, but it now has some oscillations. It's going to oscillate a bit before it settles. So let's add this to our plots here. We have 2 square root of 2j, and we have -2 square root of 2j. And what is the real part again? It's -1, right? Yeah. So -1 here. So we have poles here and there. And then this gives an exponential with a sinusoidal that are decaying like that. So that's the next case. Okay, we good? Any questions? Okay. The last example is for b equals to 6. And when b equals to 6, we'll have a critically damped system. For a critically damped system, we'll see the two poles at the same point, and then we shall see also an exponential waveform as a result of that. I will post a solution for that one later. We'll just add another point to our graph here, around 3, 2 poles at the same location, and then you still get that waveform.